In this lecture, we will consider modal solution methods. Up until now, we've primarily talked about physical coordinates such as displacement vectors. Now we're going to change our view and use a different kind of vector basis to describe the displacements of the body. These are the eigenvectors themselves of a freely vibrating system without damping and without external force. So this set of eigenvectors forms a convenient vector basis. The nice thing about it, like a Fourier series, is that the longer wavelengths components are more important, and these correspond to lower frequencies for us. So if a person can carry a certain number of the eigenvectors as base vectors, you can concentrate on the smaller frequency end of the spectrum where the wavelengths are the longest. Vehicle industries such as automotive and shipbuilding, aircraft often use modal methods because the structures are so large that they can't really contend with all the physical degrees of freedom. A driving factor here is that the finite element model is usually so large due to the geometric requirements to point out all the holes and bends and curves in the surface that by the time you get to a dynamic solution, you really have too much fine detail in the problem. So using modal methods is a way to take a look at the more important forms of motion of the structure, namely the lower modes. I'll give a little bit of an overview to start. Then we'll discuss the use of eigenvectors as base vectors. We start out considering the academic case where you would carry all of the eigenvectors as degrees of freedom. But then later we soon learn how to truncate and reduce that set to a manageable set of vectors. For instance, in an automobile study, a study might consider the first 50 modes in a vehicle structure that might have hundreds of thousands or even 1,000,000 degrees of freedom. We'll check the damping and how that enters. Then we will look at an example problem for modal frequency response. This is a good application, and we'll repeat our lab problem where we had done this previously with direct frequency response, and that means using the physical coordinates. We'll just mention modal transient response because we're not ready to really do that type of work yet, and then I do some problems in the problem session. Normal modes are used to solve a number of practical response problems. Here's a list of the solvers within Nastran, both for direct solution and modal solutions. The three that we are concerned with today are these bottom modal methods. But to start off, let's mention that we do normal mode studies to get the base vectors. That's the solver 103 in Nastran, and we had a lab on that. Then you can do direct frequency response. We did that in our lab number 6. You can do direct transient response, and that will be done in our lab number 7. We haven't done that one yet. Complex eigenvalues can be found directly. I only look at this once back in the lecture on robotics where we look at stability of a robotic system. Anyway, that's a solver 107 in Nastran. But what we're interested in today is modal frequency response and solver 111, and that is our current lecture. We won't get into modal complex eigenvalues nor modal transient response, but I think you'll get the basic idea out of looking at modal frequency response. Let's review the normal mode process because those normal modes are our base vectors, as if in a Fourier analysis. The undamped system equations of motion are shown here. These are ordinary differential equations. They're second order. This is a matrix form. We know that the mass matrix M and the stiffness K need to have certain properties in order to ensure correct solutions. For instance, we want the mass matrix typically to be real and positive definite and symmetric. The stiffness matrix normally is a real symmetric matrix and positive semi-definite. If there are some rigid body modes possible, then those correspond to zero frequencies, and that can happen. So K might be semi-definite. The solutions that we've identified, we use these special symbols for. We have the frequencies omega and then the corresponding mode shape phi. I'll use a subscript to show which of the normal modes it is that you're speaking of. And here I've listed 3 of them, but in an n-dimensional system you will have n sets of eigenvectors and frequencies. So it's clear that there's just a very enormous amount of information here in the normal modes. If you had a 30,000 degree of freedom system, you would in principle have 30,000 eigenvectors. According to Rayleigh and his earlier thoughts, at least half of those are bogus because the system can't accurately describe the top half of those. But the lower modes are generally fairly important physically and mathematically. What we do then is form a transformation matrix where we stack up the lower modes. So these are the phi vectors shown here, and I show 1 up to some number n. And if you carried all of these, they would form a complete set, if n indeed is the size of the set of equations. Normally, though, we will truncate and take only a subset of these vectors. But there are some mathematical theorems about these eigenvectors. They are orthogonal. They so-called span the space, which means that they're a complete set of vectors equivalent to the use of Fourier analysis, say, in a time history like used by the electrical engineers to analyze voltages and current. So these will be our modes that we will use to represent the total problem. We'll use these base vectors now as a way to represent the entire problem. The physical nodal displacement vector is transformed by using the eigenvectors then as these base vectors. The C quantities are generalized coordinates or participation coefficients. I'm showing this set of coordinates going up to lowercase n, and we will consider that to be the size of the original problem, say 30,000 equations. So this is meant to be a full transformation and not truncated. And you find that when you have a set of vectors in column form as shown here, then the participation factors, or these generalized coordinates, are a post-multiplying vector on the back here. Then you make that substitution into the original physical equation of motion, where the acceleration, velocity, and displacement vectors are expanded in terms of these normal modes, as shown below. And this is a set of n equations and n unknowns. You could solve this as it stands, but there are some good, strong reasons for converting this into more of an energy notation rather than a force notation. Currently you have a set of equations which in a structural theory alternately describe translations and rotations, and this is often not numerically well posed. The accuracy can suffer. So it's better to continue, as we will in the next slide, and use a Galerkin type approach where we convert each of the equations into an energy balance, and then you get a better numerical solution. This energy approach seems to be called Galerkin's approach by many authors. I'm not certain why, except that in the integral forms of this, Galerkin did do this early, where he posed error in the form of a force on balance and then multiplied by the displacement-like quantity and created something that was energy-like and integrated it over the entire body. Now we have a matrix form here, and we're going to take our force-like equation, and by that I mean there's alternately forces and moments are the balance that you're imposing, and then we're going to pre-multiply by displacement. There's no integration involved, it's just a matrix approach, but I'll still call this a Galerkin energy approach here. So we pre-multiply by the transformation matrix in a transpose form, and this becomes a bunch of row vectors, and they go up front of each of the terms that we've got. This also modifies the force vector on the right. What you've got now is reminiscent of a Lagrangian dynamics formulation where you look at the work that can be done by the force field on certain degrees of freedom. And here, this is indeed the inner product of displacement vectors times a force vector, and it gives you what are called generalized forces here on the right, which characterize how much work can be done by the force field on each of the eigenvectors. Now the other terms on the left have this triple product, which we will identify respectively as a generalized stiffness, a generalized damping, and a generalized mass. And this, in the kind of work that we do, if you have real symmetric, positive, definite matrices, you find that you can prove that the generalized mass and stiffness are diagonal matrices. And that's due to the orthogonality of these mode shapes with respect to both the mass and the stiffness matrix. So this really is an orthogonality statement that I'm collecting here at the bottom. And then I'll use these script characters M and script K for those generalized quantities. The damping matrix is generally chosen to be such that it diagonalizes the generalized damping matrix. This can be done by choosing proportional damping or using Caughey's criterion or simply measuring the damping in each of the modes. One way or another, people often will come up with a diagonal damping matrix script B called generalized damping. Then the full set of equations appears as shown next, where you have diagonal mass, damping, stiffness matrices, and then that same process has caused this inner product between the physical force field and the normal modes here, now arranged in row form. And this is an energy type of statement because it shows how much work can be done by the force on each of the normal modes. You then get this set of scalar equations which can be solved sequentially. They don't have to be solved simultaneously. This can be solved for transient motion or for harmonic or any other kinds of situation you would like, response to initial conditions and so on. The uncoupling that we've gotten implies that the modes are synchronous, which means that they do not pass information from one mode to the other. That's why you're able to consider them separately. Physically, the mode shape as it moves in time is such that the entire displacement field passes through zero at the same instant of time. So that's what the synchronous word means. Now the problem with the preceding derivation, where you carried all of the modes as generalized coordinates, is that you get too large a set of equations. N equations and n unknowns is just too many for a set of 30,000 equations, let's say. So the practical alternative involves condensing down the physical coordinates into a reduced set of generalized coordinates. It's possible to do that with so-called nodal condensation methods. What we will next talk about here is modal condensation. This is a truncation process where instead of carrying all of the normal modes as base vectors, you only carry a set of, say, m of those vectors. And this then gives you, at the outset, a set of n equations in m unknowns when you make that same substitution that we did earlier for the acceleration, velocity, and displacement. This, again, is where Galerkin's method can come in to help. So we pre-multiply by the displacement-like vector, which is the row-wise set of eigenvectors shown here, and I'll carry the subscript for the truncated set of eigenvectors. Again, we get a diagonal matrix for the mass, and then uncouple that into this scalar equation. We've also gotten diagonal damping by assumption and diagonal stiffness matrices. The generalized force is again the projection of the force vector onto the limited set of normal modes that you're using as base vectors. So we result this time in only m scalar equations here, which can be solved, and they can be solved one by one. It isn't obvious, but the generalized mass and stiffness terms are the same, at least comparing term by term, with those that appear in the full set. And why would that be? Well, it has to do with the orthogonality. There's no interaction between those modes, nor in the inertia effect, nor in the stiffness effect. So, interestingly, when you use a reduced set of vectors to represent the system, you get the same resulting participation coefficients for those lower modes, and they're not affected by the absence of the upper modes. There are some methods that try to accommodate for that truncation. Those are often called dynamic condensation methods that are, and they're higher order methods. But the approach we show here is the straightforward truncation. I'll repeat that we call this a modal condensation in contrast to the nodal condensation methods that we study later. Let's review the two kinds of damping that we've previously mentioned: proportional damping by Rayleigh, and then Caughey's form of synchronous mode damping. The proportional damping is where you assume that the original physical matrix for damping coefficients in physical coordinates is proportionate to the mass matrix and the stiffness matrix, where alpha and beta are just constants of proportionality. And many people just call this Rayleigh damping. If you put this form of B into the full equation of motion and then do a coordinate transformation, as we've done before, to the modal coordinates, Xi, you get this expression. We previously showed that the stiffness matrix and the mass matrix over here are well behaved and become diagonal. We've got these new terms, though, here where the damping is considered, and by using the distributive property of matrices, we can bring those two into two separate factors. In the front, we'll get the alpha coefficient times this mass matrix, and that turns out to be the generalized mass matrix, which is diagonal. The beta proportionate term comes over here and multiplies the Xi dot as if it were a stiffness. Now, these are appropriate, it turns out, when this is a structural type of damping here, and when this is a viscous type damping here. We will simplify the notation and show the uncoupled scalar equation. Now we have the generalized mass terms appearing in two places and the generalized stiffness term appearing in two places. This equation can then be integrated by a number of different ways, and we'll speak about those methods later. If we move to Caughey's criterion for these synchronous modes, he found a necessary and sufficient condition that I repeat here. This is awfully good to prove whether or not your damping matrix will in fact uncouple the system. It's less useful as a working tool to create these B matrices. I think we have to view this as a bit of an academic point, but it was really of great interest to those of us studying structural dynamics when this came out. Tom Caughey was on my doctoral committee at Caltech, and so I got to know him a bit out there. He was just a wonderful person and did so many creative things in the dynamics area. These synchronous modes deserve maybe another discussion figure. We mean that the various portions of the body are either in phase, such as rising upward, like these plus regions that I'm marking, or they're out of phase by 180 degrees, moving downward there. And the entire body will pass through the zero deflection position at one instant of time. So you do not get the contrasting case, which are traveling waves, where you get zero crossings that sweep over a body. And that's more typical of non-conservative vibration problems such as panel flutter or flag waving. You've probably observed flags waving in the wind. Those are not synchronous modes by any means. Those are traveling waves. You can show that you can get a standing wave by a proper mathematical superposition of two traveling waves going in opposite directions and then having those waves reflect in a prescribed way off the boundaries. So the two kinds of waves are related, but in a way that is rather mathematically intricate. Well, anyway, this leads us to these uncoupled equations of motion that we have discussed. And so this becomes a generalization of the normal mode concept for an undamped system, that now you get these so-called synchronous modes in the case of the damped system. And it's probably easiest to think of those damping terms in the formulation that Rayleigh gave, or by checking them by Caughey's proposal, when there really is damping, physical damping distributed through a system. But as I'd mentioned, more often nowadays I think people just assume modal damping, or they can measure it. Modal damping is used a lot in the vehicle industries, for instance for aircraft. So far we've defined this as somewhat of an analytical concept, but it does have good experimental basis. And if you have these uncoupled equations, and if you put harmonic forces here on the right side, you can then check the vibrations on the left. If you can resonate this system and find some peak amount of response, you can figure out what the damping is like. Here I've shown a viscous form, or you can put it in a structural damping form, and you can go back and forth between those. And I think I've mentioned earlier that codes such as MSc and Nastran let you read in structural damping as a function of frequency. So what you might do then is measure the damping in the various lower modes of the structure, you know, at 8 Hertz, 12, 15, whatever those resonant modes are, and then make a plot of that. And generally speaking, your damping will tend to drive out the higher modes, so the lower ones are the more important ones. If it were truly structural damping, you'd have a plot of G versus frequency that would be a straight horizontal line, but there are sloshing effects, there's elastomers, there are a lot of things in the body that might not allow it to behave purely structurally. So you get some sort of a hybrid combination of effects that ends up somewhere between viscous and structural damping. So far we've been talking about the modal solution method as a way of attacking a placid structure which has a little bit of damping in it, and we tend to use the normal modes of the undamped system as our base vectors. The approximations involved are that you usually have to truncate the system in terms of how many modes you carry in your representation. So there's a you ignore some of the high frequency content and short wavelength behavior. Another way to use this modal solution approach is when you have a strongly non-conservative system where there's more than passive damping in it, but there might be controlled system forces or aerodynamic forces that are non-conservative in nature and feed energy into the structure or take it out. Now, even with the air off, you might have such control forces on an airframe, let's say. But you can still go back to the set of normal modes where you have no non-conservative forces, no Coriolis, no centrifugal, and so on, and use those as your vector basis. So in other words, if you solve this energy conserving problem first, you can then use that to solve the larger problem where you bring in all of these exotic velocity dependent terms, all of these exotic stiffness terms. Follower forces, flutter situations involve aerodynamic stiffness. Usually the mass matrix is not very wild, so it's not that kind of a guy. It stays home and follows the rules. But damping and damping and stiffness terms are the ones that can go berserk and cause a lot of trouble. So you might wonder, how in the world could you use this modal method for that? Well, if you carry enough modes, you're still representing the spatial distribution of displacement fairly well, and it becomes like a Fourier series analysis where those are just approximations to the true displacement fields. But it works, and you can do a truncated version on this, or even a full modal solution if you've got the patience. I'd like to do a numerical example now of a modal response solution. We'll do it for frequency response where the input force is harmonic. And we'll use a truncated transformation where we only carry some of the lower modes. Then the equation of motion is shown here. I've left it so far in the form where there's a general damping matrix. Because the external force is harmonic, we logically assume the response is harmonic. So we pick our generalized coordinates varying as the expression shown here, where you have all of the shapes of the body responding at the frequency omega. Now, this is not quite obvious then, because what you're saying is, in this frequency response approach, that the frequency is set for all of the modes to follow the external force. This is not like a transient problem where you hit it and it rings in all the different frequencies. This is a so-called steady state solution where you follow as the external force dominates with this capital omega frequency rather than the lowercase omega. This is the equation of motion then, and we've struck out the time dependence. We're left with the frequency still appearing, of course. Here's our damping to be resolved yet, and we do that below here by saying that we'll use modal structural damping. And so when this equation uncouples, shown here for each of the modes, we assign a G sub I as the structural damping in that particular mode. You can group the terms as shown here, and then this can be solved one at a time. Let's now apply the modal solution method to a response problem. We're going to rework our Lab 6 that we previously did by a direct solution. This was a steel cantilever beam, and it has a tip load oscillating with 1,000 newtons as shown. We're going to allow that force to vary from 2 to 18 hertz, and we'll set the damping coefficient G to be 0.05 over that whole frequency range. So that's equivalent to saying that we're going to have the same damping in all of the modes. With our modal solution, we're going to carry all of the eigenvectors as base vectors. There are going to be 4 of them when we get to our modeling and have a 2-element model. We're only going to consider flexure in the XZ plane, and we're not going to try to represent the flexure in the XY plane, nor in torsion, nor in axial deformation. Just to be on the safe side, we'll consider the frequency range all the way from 0 to 2,000 hertz when we're searching for our normal modes. But we know that the 4 frequencies that will be represented in this problem are all within that range, well within that range. This problem makes one think a bit about a fundamental question, and that has to do with the frequency range over which you find normal modes compared with the frequency the response problem is going to excite the problem in. And basically you're trying to compare a spatial problem with a temporal problem or a time problem. Those 2 frequency ranges might normally be related. In our case, the wavelength of the spatial behavior due to a tip load is probably going to be a rather long wavelength behavior. In general, though, it would be possible to get short wavelength behavior by having forces that pushed and pulled at small distances apart and cause this beam to actually flex into short wavelength behavior. And so this is a complicated question, and a lot of people worry about this a lot. Just think of it in terms of Fourier analysis, and think that there's both the space and time problem here, and we want enough terms so that we can calculate accurately the spatial wiggles that the beam makes, and that is related to the modal frequencies of the normal modes that you use. So I'm on dangerous ground here talking about kind of an advanced topic in an introductory course, but let me just leave it that this is a tough problem, and think about it a little bit is over what frequency range should you get your normal modes when you're looking for response in another frequency range. Our finite element model is developed here. I'm just going to use 2 elements as previously for simplicity and ease of data entry. We will constrain out the unneeded degrees of freedom so that the other modes don't even enter. We'll use modified givens for extraction, and here's a picture of the G, the damping coefficient, as a function of frequency. When we do our data preparation, then I will put in red the changes from our previous solution, and it will be the same type of identification. I'm asking for 5 minutes, which was pretty ample. The solution is 111 this time, modal frequency response. Now I'll show the case control commands. And a change now is to give a method here, and that's needed for the eigen problem, and it points below to an eigensolver. We're interested in our displacements with the phase relation so we can get frequency response figures of magnitude and phase angle. Here's the dynamic loads that will be used in the actual run, the response run, and here we have our damping. 21 is a flag to point to our structural damping down below. We're going to plot some output which have to do with the deformed deformation at the different frequencies. That was done before, and there's no change. The next figure continues the case control commands, and these are the rest of the plotting commands. We ask for frequency response plots of both the magnitude of the displacement out at the tip and the phase angle at the tip. Then we go into bulk data entries, and these are the same as they were in Lab 6. Again, we're only going to ask for vectors that lie between 0 and 2000 Hertz. But knowing where those are, we realize we're asking for all of them. So we'll get all 4 normal modes through this process. Let's finish our bulk data entries. The physical properties of the beam are the same as before. Now here we have the this load, and it's got an amplitude governed by the D area card of the 1000 newtons, and then here's a table for the load as a function of frequency. I'm going to define it from 1 to 20 Hertz, just over the range, to cover the range that we are exciting the beam at. So that's the actual response frequencies. Then here we have the frequencies that are going to be This problem was run on a Hewlett-Packard workstation, and then the results were presented as shown here. I'll start with the sorted bulk data shown here. And here are the nodal displacements, and we're interested in the tip displacements. We show this as a function of frequency, and so we're interested in this T3 value primarily here to see how it changes through the resonant point, and we're reaching a maximum of some 18 millimeters here. I'll collect the data for the tip displacement and compare our current solution using a modal process against the earlier direct solution. And we find that, lo and behold, these two give the same answer. So at first you say, wow, is this ever accurate? Well, it ought to be accurate because we used all 4 of the normal modes in the problem to solve the problem. So there was no error due to modal truncation in this case. Now, the fact that you're getting the same answers means that you have the same modeling error baked into each of these 2 solutions. These both will be inaccurate to some extent because the modes that we're using are not the true modes. We know that the frequencies were substantial. To further emphasize how we got the same answer as previously, I'll give you a frequency response plot. Here's our tip displacement, and the 2 figures lie directly on top of each other for the direct and the modal solution. And we're not surprised by that. Now I'll just end with a couple comments about the method. Our frequencies had been calculated earlier by the Givens method, and we repeated that as a part of our current modal response process, and so the frequencies were correct to all significant figures, but as I mentioned previously, have the same modeling error baked into them due to only 2 elements as the previous direct run had. So we got exact comparison of 2 approximate methods. The MSc Nastran program uses an uncoupled solution algorithm. So when you do use these modes, and it's able to break that down into the sequential solution of a set of ordinary differential equations, in this case even algebraic equations, where the inversion of the complex mechanical impedance is used. So rather than a simultaneous solution, you do a sequential or an uncoupled solution of equations one at a time. Finally, we won't do a modal transient response. We haven't had the transient integration explained to us yet in this series. You'll get that in a few lectures. So we do need those ideas. This method also leads to uncoupled transient equations rather than the uncoupled really algebraic equations that you do solve for the frequency response problem. I like to give small numerical examples that can be worked out by hand to illustrate these more exotic computer-based solutions. So for the modal response problem, I'm going to give a small problem based on our Lab 6 geometry. The problem's complicated enough that it takes two figures to state what the problem is. On this first figure, I will illustrate that we have this beam, which I'll tell you is basically the beam that we've looked at before. There's a force which has a vertical component both at the tip and the mid node and in opposite sign sets. So when this one is up, this one's down. That will tend to excite a little shorter wavelength behavior in the structure. The structure will oscillate between these two extreme envelopes, where this is a cantilever beam clamped at the left end. Now the frequency is given as 180 here, and you know that that is I cap omega t. So we have that cap omega is 180, and that dimensionally is in radians per second. So you can figure the frequency out from that. To complete the physical description, I need to either give the physical characteristics of the beam or give them in generalized form. Here I give the generalized mass and the generalized stiffness. You can tell that there has been a mass normalization in this problem because we get unit values for generalized mass. Here are below the resulting eigenvectors that are given as a part of the problem. Notice that they are not normalized with the unit maximum value, but rather have been normalized by that mass normalization as I mentioned. You get some feeling for the physical numbers here as these are entered. And for those of you who know the theory, you understand that these terms on the generalized stiffness are related to frequency squared, but you have to have the proper units to make that make sense. We're carrying all four vector components. They're in column form, and those are the only four eigenvectors for our flexure problem in the xz plane. So this again ought to be an exact answer if we carry all four modes. If we decide to truncate and only carry out a two-mode solution, and that actually was stated, then we have an approximate solution. And in that case, we just mean that we're taking these first two modes and throwing away the information in these higher two modes. Now we need to solve the uncoupled modal equations. They're shown here. There's no damping in the system. Our generalized force is this inner product. We put in the proper numbers here, so we have our column vectors transposed times this force vector on the right, and you get a reduced force vector here then, or a generalized force on the system. And we see that the second mode has a larger amount of work that can be done on mode 2 than the force can do on mode 1. And that has to do with the reverse nature of the load, that it just naturally fits the shape of the second mode a little better than the first. Now that doesn't mean that this second mode is going to dominate the response, because it takes more energy for it to move, more kinetic energy. So we will see how the battle proceeds here. Let's now write out the differential equations of motion. Here's our newly found force on the right, and it's at roughly 30 Hertz. The system is on the left here. We're going to assume that it responds in a steady state way also at the roughly 30 Hertz level. So we'll assume 180 radians per second on a set of modal participation coefficients here. When we uncouple the equations and solve for the first participation coefficient C1, we're able to solve for that and find this value. It comes out negative. If you think about it for a second, that makes sense. We're driving this system at roughly 30 Hertz. That's above the first frequency, which is near 10, and below the second one that's near 50. So we're driving this system above its first natural frequency. And you can see we have this out-of-phase behavior. One might be tempted at this point to think that the tip load is doing less work and that somehow the midpoint node is driving the system in this case. And that would be true if this was a quasi-static problem or below the first resonant frequency, but we're above. And remember, in a single degree of freedom system, you get that 180-degree phase reversal. So this is not unexpected. This is a reasonable result for the contribution of the first mode to this dynamic motion. Now let's solve for the participation of the second mode. We do the same thing as we did before, uncouple the second equation of motion and solve for C2. And when we do, we get this number. Now that number is a little bit smaller than the earlier one, and so we see that the second mode will not participate quite as much. Notice this time the force field is in phase at the tip with this particular mode. Well, we're exciting the system at less than the natural frequency of the second mode, so we're below resonance for that particular mode. So it kind of makes sense that you're in phase at the tip where more work is being done. Now if we'd like to add up those two results, we do that by recovering in this mapping sense from the generalized coordinates back to the physical coordinates. And if we put in a specific point on the eigenvector such as the tip, then we can get the actual numerical values here. So here's the participation coefficient of the first mode times the tip displacement of the first mode. Coefficient for the second mode times the tip displacement. And in this case, the winner is the negative quantity contributed by the first mode. So at the tip, the fundamental mode, that is C1 and Phi1, is dominating the motion. Remember that this is a half amplitude, and when we put these bodies together, I didn't really plot out the full shape, but it appears to be going down at the tip, so it would go something like that. And then if I'm a good sketcher, this would have to come back down this way and go back up. So as always, we're looking at an envelope of the motion. For our second problem, let's look at damping and look for existence of synchronous modes. We'll look at both the Rayleigh and the Caughey forms of the condition for that to happen. I'm going to propose this mechanical system with 2 degrees of freedom with this inertia matrix, damping matrix, and stiffness matrix. The first question is whether the damping matrix is a type of Rayleigh proportional damping. And then secondly, does that damping matrix satisfy Caughey's condition? Showing whether a damping matrix is of a Rayleigh type is actually straightforward, because You just see if you can solve for the proportionality coefficients alpha and beta that make that approach work. And here's the general statement. I should put a question mark up here. Is it true that you can decompose this matrix into these two terms? Now, this is not arbitrary in a sense, because there are two unknowns and there are three coefficients here that have to be balanced. Because of symmetry of this matrix, there are only three independent terms. So this won't happen in all cases. The first thing that might have occurred to you is that, well, it always works out. No, it doesn't. Let's check it though. The first equation, the upper left coefficient gives 3/10 as alpha plus beta, and then the second term gives 7/10 equals 3 alpha plus 2 beta. Those are solved simultaneously and you do get a solution. So far so good. But now you have to check the third equation, the third independent equation here. 2.2 equals 10 alpha plus 6 beta. And when you do that, you find that that's identically satisfied. That's kind of a compatibility equation. So yes, the answer is that damping matrix up here is a Rayleigh type of damping, of proportional damping. The second question we're asking is whether a kind of proportional damping that satisfies the Rayleigh law is also a Caughey type of damping. Now, the Caughey formula is the necessary and sufficient condition, and in a sense it's the weaker of the conditions in terms of what it requires of the damping matrix. And with some thought you would realize that all Rayleigh damping must be also a Caughey type. In other words, if Rayleigh, then Caughey. And we can work that out theoretically first before we plug the numbers in. I'll make a little theorem here. Any Rayleigh damping matrix satisfies Caughey's condition, and then I prove it. This is kind of a fun thing. I've never seen this in any textbooks. You put in for the damping matrix at the front and at the back the Rayleigh proportional damping, and then you start matching terms and canceling them. You get both the mass and mass inverse term on the left here and on the right, which cancel, and then the stiffness term here that cancels. And so in fact you get that the Caughey equation is satisfied. So it is true, any Rayleigh damping matrix also satisfies Caughey's condition. But Rayleigh's is easier to work with, and that's why people still use it a lot when they want to discuss academic problems. Now let's work out the numbers for our specific example and see that Caughey's criterion is satisfied. To do this, you need the inverse of the mass matrix, which I do here, and then I directly form Caughey's condition here. You turn the crank, and I do it by first multiplying the second pair of matrices on this side, and I do over here a product of the first two, getting a little creative here, into this. Then you finally multiply those two on the left, those two on the right, and lo and behold, it does work out. So, at least in this specific case, we show the reduction from the Rayleigh criterion indeed also satisfies Caughey's, and then we had a theorem that shows that that always happens.